Welcome to the deep dive. Today we're unpacking a really comprehensive set of source materials. Specifically, we're looking at a detailed Wikipedia overview of demining.
Yeah, and it's a fascinating topic because it sits right at the intersection of military history, cutting-edge science, and just sheer human resilience.
Exactly. And to kick things off, I want you, the listener, to picture this terrifyingly simple economic asymmetry. Manufacturing a landmine costs, anywhere from $3 to maybe $75.
Right, which is just a trivial amount of money for what it actually is.
Exactly. It's a piece of plastic and high explosive designed to just sit silently in the dirt for decades. But removing that exact same device safely, that flips the economic scale completely.
It really does. I mean, you're looking at costs ranging from $300 to $1,000 per mine just to get it out of the ground.
Which is mind-boggling.
Yeah.
And that financial disparity is, well, it forms the crux of this entire humanitarian nightmare.
It's what makes this an invisible 500-year problem. And the source material we're diving into today outlines not just the grim math of the crisis, but the absolute extremes of human ingenuity mobilized to solve it.
We're talking wild stuff here. Everything from repurposed space shuttle fuel to giant rats and genetically modified botany.
It's incredible, but I think, setting a calm analytical tone here is important because we really want to understand the mechanics of this threat first.
Yeah. Let's jump straight into the engineering evolution. Since you guys are probably well aware of the historical shifts from anti-tank to anti-personnel mines, we don't need to rehash the basics. But the traditional image of a heavy metallic disc that's largely outdated now.
Totally outdated. Modern clearance challenges are all about evasion. The materials have evolved specifically to evade detection.
Right, leading to what they call minimum metal mines.
Exactly. We are talking about polycarbonate, plastic, or wooden casings, and they contain as little as a single gram of metal.
Which might just be the firing pin, right?
Yeah, just the firing pin. And that shift away from ferrous materials, it creates an immense physics challenge for anyone trying to locate them.
Because conventional metal detectors rely on electromagnetic induction.
Right. And that requires a substantial metallic signature to disrupt the magnetic field. When you reduce that signature to 1 gram, the device becomes practically invisible.
Especially in highly mineralized soil.
Exactly. And this leads to the daunting global math presented in our sources. Current estimates suggest there are roughly 45 to 50 million landmines scattered across approximately 60 countries.
45 to 50 million. And the clearance rate is the part that truly stops you in your tracks. The global effort right now removes about 100,000 mines a year.
Yeah.
So doing the rudimentary math there, that reveals a 500-year timeline just to clear what is currently in the ground. And that's assuming no new conflicts arise.
But, and this is a crucial analytical point in the source text, there is a massive caveat to those terrifying figures.
The estimates are often way too high.
Right. Initial wartime estimates are notoriously inflated. In the chaos of active conflict, deployment records are either destroyed, falsified, or they're simply never kept.
Especially when they're just scattered indiscriminately from aircraft.
Precisely. Mozambique is a perfect case study for this discrepancy. Early operational estimates suggested several million mines were buried across the country.
Millions.
Millions. But after the vast majority of the clearance operations actually concluded, the real number recovered was around 140,000.
Which is still a tragedy, but statistically a massive difference.
A huge difference.
But the psychological terror remains exactly the same. I mean, a farmer doesn't care if there are 10 mines or 10,000 in their province.
Yeah.
A single suspected device in a field renders that entire tract of land agriculturally and economically dead.
Until it is definitively proven safe.
Right. And that brings up a fundamental distinction in the source material regarding methodology, the stark difference between military breaching and humanitarian demining.
They're entirely different operational paradigms. Military demining prioritizes momentum and survival above all else.
Because combat engineers, sappers, they're typically operating under active enemy fire.
Exactly. Their objective is to breach an obstacle to maintain maneuverability. The sources note they might have an operational window of merely 7 to 10 minutes to clear a path.
Wow. 7 to 10 minutes.
Yeah. So in that tactical environment, missing a few devices on the periphery, that's an accepted actuarial risk to prevent the entire column from being targeted by artillery.
Speed is survival. But humanitarian demining operates on the complete opposite end of the risk spectrum.
Right. The mission objective there is perfection.
100% clearance.
Dictated by the International Mine Action Standards, or IMS. The goal is complete clearance to a specified depth, guaranteeing that a child can play in that dirt or a farmer can drive a tractor over it without hesitation.
You cannot just clear a narrow path. You have to thoroughly sanitize the environment.
And achieving that mandated perfection relies on agonizingly primitive techniques.
This is the part that blew my mind. Despite all our 21st century tech, the conventional method heavily mirrors the Polish mine detector invented back in World War II.
It really hasn't changed much. Deminers are systematically sweeping an area, and upon receiving a signal, they resort to manual prodding.
They literally insert a rigid probe into the soil at a highly specific 30-degree angle.
Yes.
And the mechanics of that 30-degree angle are both fascinating and terrifying. The Deminer is probing the lateral sides of an unknown object, feeling for the texture of a synthetic casing.
Because if they probe vertically,
Right, or at too steep an angle,
they risk applying that fatal downward pressure.
which for an anti-personnel mine is just 2 to 11 kilograms of force.
Tragically, the weight of a small child.
Yeah. And they're doing this for hours on their hands and knees in sweltering heat.
And the physical danger is compounded by staggering operational inefficiency. Former combat zones are inherently littered with metallic debris.
Shrapnel, bullet casings.
Destroyed vehicles, unexploded ordnance. It creates an overwhelming signal-to-noise ratio. The data shows that for every single legitimate landmine discovered, deminers excavate between 100 and 1,000 false positives.
I want to pause on the economic devastation of that false positive rate. I was reading this section on the Cambodian Mine Action Center, and they tracked their operational efficiency over a 6-year period.
That data is a sobering metric for the entire industry.
The sheer volume of wasted human capital is hard to fathom. Over that 6-year span, their personnel spent 23 million hours performing manual excavations.
23 million hours.
And 99.6% of those 23 million hours were spent digging up harmless scrap metal.
You're looking at an entire generation of labor diverted into excavating junk just to find the fraction of a percent that could actually kill someone.
Hearing a statistic like that perfectly contextualizes the pivot toward brute force mechanical solutions. If manual clearance is that agonizingly slow, you scale up the machinery.
Exactly. You bring in the massive mechanical flails.
Heavily armored vehicles derived from Sherman tank chassis, right?
Yeah, equipped with rotating drums that violently thrash the earth with heavy chains to intentionally detonate devices.
And heavy machinery just mitigates the false positive issue entirely by ignoring the finesse of detection. It moves straight to kinetic destruction.
Organizations like the Halo Trust extensively utilize heavily modified agricultural tillers and excavators.
They up-armor them and use massive attachments to just churn the soil.
They crush the polycarbonate casings and trigger the explosives safely away from the operator. The operational data indicates these mechanical assets can clear and destroy mines roughly 7 times faster than a manual team.
7 times faster. But the most compelling examples of mechanical adaptation aren't even coming from well-funded international NGOs.
No, the source material highlights the sheer resourcefulness of Ukrainian farmers in 2022 and 2023.
Facing heavily mined agricultural land and the immediate pressure of planting seasons, they couldn't afford to wait for international clearance teams.
So they engineered their own remote-controlled clearance vehicles.
Stripping rugged armor and drive components from abandoned Russian military hardware and welding them onto standard commercial tractors.
Human resilience invariably accelerates engineering when livelihoods are directly threatened. But machinery has profound limitations.
Right. Excavators and flails require relatively flat, accessible terrain.
They are completely useless on steep mountain slopes, in dense jungle undergrowth, or in waterlogged environments.
So when heavy engineering fails, the industry pivots toward biological detection systems.
Nature's bomb squad.
Exactly. We transition from diesel engines to the olfactory bulb. And the detection dog is the historical gold standard here.
Their olfactory sensitivity is staggering. They are capable of detecting explosive volatile compounds at concentrations up to 1 million times lower than human capability.
1 million times.
Mm-hmm.
They're smelling the microscopic chemical vapor leaking through the seals of a buried mine casing.
But canine units bring significant logistical friction. The unit economics are challenging. Training a single specialized mine detection dog costs approximately $10,000.
And beyond the capital investment, you're dealing with a biological asset that gets tired.
Suffers from fatigue, requires extensive quarantine protocols across international borders, and experiences degraded performance in extreme heat or heavy rain.
Not to mention the psychological toll. A dog navigating a dense minefield can easily become overwhelmed by the sheer volume of chemical signatures.
But the source material outlines a brilliant logistical workaround for this called the REST method, remote explosive scent tracing.
Instead of forcing a fatigued animal to navigate a sweltering, dangerous field, they bring the field to the dog.
Precisely. Field technicians utilize specialized vacuum equipment fitted with polymer filters to draw air samples from designated sectors of land.
Those filters trap the volatile explosive molecules.
And then the filters are transported back to a highly controlled, climate-regulated laboratory environment.
Where the dogs can rapidly interrogate the samples without physical exhaustion or distractions.
It dramatically accelerates the initial surveying phase of large tracts of land.
But if the canine logistics seem complex, the deployment of giant pouched rats sounds entirely absurd until you look at the underlying biology.
Yes, APO, an NGO based in Belgium, trains these rats in Tanzania. They call them Hera rats.
And the economics immediately improve compared to dogs.
Significantly. The training pipeline for a giant pouched rat is roughly $6,000, presenting a great upfront cost reduction.
But their true operational advantage lies in their physical specifications, right?
Exactly. An anti-personnel mine typically requires a minimum of 2 to 11 kilograms of downward force to detonate. These rats are exceptionally light, hovering well below that trigger threshold.
So they can physically scurry across an active pressure plate without initiating the firing sequence.
And the psychological differences between the rats and the dogs solve a major deployment bottleneck. Dogs form intense emotional bonds with specific handlers.
If a handler gets sick or rotates out, the dog's operational effectiveness plummets.
But the giant pouched rats are highly food motivated and lack that deep emotional attachment. You can ship a trained rat across the globe, pair it with a new local technician, and it will immediately start working for a banana reward.
For banana, that's amazing. And returning to the Cambodian scrap metal problem, the rats offer a biological filter against false positives.
Because they have zero interest in ferrous metals.
They're strictly hunting the vapor signature of the explosive compound.
The operational metrics are remarkable. A rat can effectively clear an area in a single day that would occupy a manual technician with a metal detector for 2 entire weeks.
Harnessing mammalian biology makes intuitive sense, but the entomological applications take this to an entirely different level. The research surrounding honeybees is a masterclass in exploiting existing ecological mechanics.
It really is. Scientists realized you can condition a hive of honeybees to associate the chemical scent of TNT with a sugar syrup reward in the span of just 1 or 2 days.
1 or 2 days of training.
And the mechanical collection process the bees utilize is brilliant. Honeybees are covered in microscopic hairs that generate an electrostatic charge during flight.
This charge is evolutionarily designed to attract and trap pollen grains.
Right. But it inadvertently acts as a highly efficient environmental mop. As the bees forage across a suspected area, those charged hairs accumulate microscopic particulate matter,
including the explosive chemical compounds leaking from subterranean casings.
They're detecting these compounds at concentrations of mere parts per trillion.
Parts per trillion. And researchers then have a few ways to read the data. They can analyze the chemical composition of the hive itself upon the bee's return, or they can use LiDAR or camera tracking to monitor the swarm in real time.
Because the bees have been conditioned to expect a food reward, they will literally hover and congregate directly over the buried mines.
Just waiting for the sugar that isn't there.
It demonstrates how rapidly biological systems can map an environment. And we see this naturally occurring without human intervention as well.
Like with the elephants in Angola.
Exactly. Following the conclusion of the Angolan Civil War, researchers observed returning elephant populations exhibiting highly anomalous migratory patterns. The herds were deliberately and precisely navigating around established minefields.
Biologists in South Africa subsequently put this to the test in a controlled study, verifying that the elephants weren't just remembering safe paths.
They were actively detecting the chemical signatures. The elephants successfully identified 96 out of 97 TNT samples.
They statistically outperformed the canine units in the trial. Now, obviously, nobody's proposing we leash elephants and walk them through active minefields.
No, definitely not.
But it underscores how rudimentary our synthetic sensors are compared to millions of years of evolutionary biology.
And that realization is precisely what is driving the current intersection of demining and biotechnology. If we cannot build a machine as sensitive as an elephant's olfactory system,
we must engineer the biology itself.
Exactly. Botanical genetic modification represents a fascinating frontier here. Researchers have focused on Thailcrus, a model organism in plant biology, and fundamentally altered its genetic response to specific environmental stressors.
The mechanics of the genetic modification target the breakdown of the explosive compounds. When TNT degrades in the soil over years, it releases specific chemical byproducts, primarily nitrates and nitrites.
And the modified Thailcrus is engineered to absorb those specific compounds through its root system.
Once absorbed, it triggers a phenotypic change, causing the plant's natural green pigmentation to shift to a stark red or brown.
The strategic vision for this is immense. You could theoretically utilize agricultural aircraft to seed thousands of acres of suspected inaccessible terrain with these modified seeds.
After the maturation cycle, drone surveillance could map the topography, identifying isolated clusters of red vegetation that accurately map the subterranean explosive contamination.
Similar synthetic biology is being applied to bacteria, engineering strains that fluoresce or glow under ultraviolet light when exposed to TNT vapors.
But the primary hurdle with biological indicators is environmental noise.
Right. No traits occur naturally in agricultural soils, potentially triggering false phenotypic changes.
Furthermore, these biodetectors are highly specialized. A plant engineered for TNT will ignore a device packed with RDX or other modern plastic explosives.
That limitation forces the physics community to develop alternative, high-fidelity synthetic sensors.
Which brings us to acoustic and seismic detection.
Right, which addresses the limitations of both biology and electromagnetic induction. Rather than looking for metal or smelling chemicals, this technology looks for acoustic impedance.
Because a buried landmine is essentially a hollow polymer container housing a dense explosive block.
And this structure possesses a radically different acoustic impedance compared to a solid piece of granite or a tree root.
To find that hollow container, technicians use specialized transmitters like loudspeakers or mechanical shakers to ping the surface of the Earth with low-frequency sound waves.
The soil and the buried landmine act like two coupled springs vibrating in response.
By utilizing precision lasers to measure the microscopic surface vibrations of the dirt, they can map the distinct acoustic signature of the hollow casing beneath.
It virtually eliminates the false positive issue caused by scrap metal.
But the absolute pinnacle of this high-tech interrogation is nuclear quadrupole resonance, or NQR.
This technology is analogous to magnetic resonance imaging in the medical field, but it operates without the massive superconducting magnets.
NQR directs a highly specific radio frequency pulse into the ground.
A pulse precisely tuned to resonate with the nitrogen atoms inherent in the molecular structure of the explosive compound itself.
It isn't just looking for an anomaly. It is interrogating the actual atomic bonds.
When the radio frequency pulse shuts off, those energized nitrogen atoms relax back to their baseline state. As they relax, they emit their own incredibly faint radio signal.
The NQR receiver catches that echo, providing absolute confirmation of the chemical makeup below. But, and this is wild, there is a profoundly frustrating vulnerability built into the physics of this multi-million-dollar technology.
The interference problem. It highlights the fragility of operating highly sensitive laboratory equipment in the real world. Every chemical compound possesses a unique resonance frequency.
And by sheer coincidence of physics, the resonance frequency for the nitrogen bonds in TNT falls squarely within the standard AM radio broadcasting band.
You can deploy a state-of-the-art atomic sensor in the field, and the faint elemental echo of the explosive material gets entirely drowned out by a local radio tower broadcasting a morning talk show.
The engineers have to develop incredibly complex algorithms just to filter out the local pop music to hear the bomb.
It is a stark reminder of the chaotic environments these clearance teams operate within. Automating that physical clearance process is the next logical step to remove humans from that chaos entirely.
We've seen unmanned aerial vehicles used for photogrammetry and route planning, but platforms like the Dutch Mein Kampf drone are pushing toward autonomous end-to-end clearance.
The architecture involves the drone autonomously generating a high-resolution 3D topographical map, utilizing a suspended sensor payload to pinpoint the anomaly,
and then deploying a specialized robotic manipulator arm. The robotic arm descends, places a small, shaped explosive charge directly above the identified threat, and the drone retreats to a safe altitude before initiating the detonation remotely.
Which forces us to look at the final critical phase of this entire operation: destruction. Locating the device is only half the battle.
Right. Neutralizing it without causing sympathetic detonations or leaving unexploded material behind requires significant chemical and thermal engineering.
High explosives like TNT are surprisingly stable compounds. They require a massive shock wave to initiate the explosive train. If you want to neutralize them without a kinetic blast, you have to attack them chemically or thermally.
On a chemical front, researchers utilize a compound called DICA. When DITA interacts directly with TNT, it initiates a rapid exothermic reaction.
The two chemicals essentially consume each other. A technician can place a vial of DTA above the mine, remotely puncture both the vial and the mine casing, and the resulting chemical reaction safely burns away the explosive filler in a matter of minutes.
But the thermal destruction methods detailed in the source material. This is where aerospace engineering intersects with demining.
Yes, a company originally responsible for manufacturing the solid rocket boosters for the NASA Space Shuttle program repurposed that exact propellant technology.
They engineered specialized thermal flares utilizing leftover aerospace propellant.
The physics of these thermal flares are staggering. They are positioned adjacent to the exposed mine casing and ignited remotely. The solid rocket propellant burns at temperatures exceeding 1,927 degrees Celsius.
Roughly 3,501 degrees Fahrenheit.
This is essentially a directed thermal lance. It instantaneously melts through the polycarbonate or metal casing and subjects the explosive filler to such extreme localized heat that the material deflagrates.
It aggressively burns away before the pressure can build to a full detonation.
The United States Navy has successfully deployed these aerospace flares in clearance operations from Kosovo to Jordan.
When you pull back and synthesize all of the disparate technologies we've explored today, the overarching narrative is a profound clash of human extremes.
It truly is. We are looking at humanity's darkest impulses. The mass industrial production of cheap, indiscriminate weapons designed to linger indefinitely.
Countered entirely by the absolute zenith of human intellect, mobilizing geneticists, aerospace engineers, and evolutionary biologists to undo the damage.
It's a phenomenal demonstration of applied science driven by a moral imperative. The objective isn't merely the technical neutralization of ordnance. The objective is the restoration of economic viability to fractured regions.
It's about returning agricultural yield to a community, enabling infrastructure development, and letting children walk to school without fear.
Establishing the baseline safety required for civil society to function. Understanding the mechanics of a Polish detector, the olfactory limits of a giant rat, or the atomic resonance of nitrogen, it gives you a window into the sheer persistence required to reclaim that land.
The scientific community is committed to a multi-generational cleanup effort. We broke the environment, and these complex, overlapping disciplines are determined to piece it back together.
Yet, as we project forward toward the eventual conclusion of this 500-year physical clearance effort, the source material forces us to consider the long-term ecological footprint.
We noted earlier that these casings leak.
Specifically, they leach a toxic byproduct known as 2-4-DNT into the surrounding soil matrix. It is highly soluble in water, allowing it to migrate far beyond the original deployment site,
persisting long enough to alter the biology of the flora and fauna around it. It is literally the mechanism that allows the bees and the genetically modified plants to detect the threat in the first place.
Exactly. Which leaves us with a highly complex environmental reality to consider. Long after the physical casings have been excavated, the thermal flares have burned out, and the minefields are officially declared clear.
How many decades or centuries will the invisible, toxic chemical ghost of these conflicts continue to silently migrate through the groundwater and ecosystems of the nations left behind?
A haunting question.
A heavy, deeply complex reality to leave you with. Thank you for joining us on this deep dive. Keep asking the hard questions, and we will catch you next time.